You know, one of the first things we learn in physics is that energy is always conserved. But is it really? It turns out the answer is kind of slippery. So today we're going to dive into this really cool energy puzzle where the solution completely changes depending on how you look at it. Let's get into it.
Okay, so check this out. This is our puzzle. We've got two blocks, a string, a pulley, a spring, and yeah, some friction to make things interesting. Now the big question is, when we let this whole thing go, does its total mechanical energy increase, decrease, or stay the same? I'm telling you, your first gut reaction might be wrong because the answer hinges on one single really crucial choice that we have to make.
All right, so to solve a puzzle like this, we got to make sure we know the rules of the game first, right? So let's start with the absolute basics.
So, at the heart of all this, we're talking about something called mechanical energy. And it's actually pretty simple. It's just the sum of two kinds of energy. You've got kinetic energy, that's the energy of motion, and you've got potential energy, which is basically energy that's stored up, like in a stretched spring or an apple hanging from a tree.
So how does this energy actually change? Well, it all boils down to this concept called work, and it's super intuitive. If some outside force does positive work on our system, like think about pushing someone on a swing to make them go higher, the system's energy goes up. And if it does negative work, like friction slowing a car down, then, you guessed it, the system's energy goes down.
In this right here, this is the secret key to the whole thing. The answer to our puzzle isn't some fixed, absolute number. Nope. It depends entirely on what we decide to call the system. To really get how this works, let's just strip away all the complexity for a minute and look at a much simpler example. Okay, so let's forget that complicated machine for a second. Let's just think about a single block falling. That's it. We're going to use this super simple case to build up our intuition from scratch.
Okay, case number one. What if we draw an imaginary little box around just the block? That's it. For this first go-around, the block is our entire system. So, what happens to its mechanical energy as it falls?
Well, if the block is the only thing in our system, then gravity is an external force, right? It's coming from the outside. And since that force is pulling down in the exact same direction the block is moving, it's doing positive work. And what does positive work do? It adds energy. So the block's mechanical energy, which in this case is pretty much just its kinetic energy, has to increase. It speeds up. Totally makes sense.
All right, now hold on. Same exact falling block. Nothing has physically changed. But this time, let's just change our point of view. What if our system is now the block plus the Earth?
Whoa, okay. See what happened? The moment we include the Earth in our system, gravity is no longer an external force. It becomes an internal interaction between the two objects. And suddenly, there are no big external forces doing any work on our system, which means the total mechanical energy has to be conserved. As the block falls, sure, its kinetic energy shoots up, but its potential energy drops by the exact same amount. The total amount in the bank stays the same.
So just look at this side by side. This is so cool. It's the exact same physical event. A block is falling. That's it. But just by changing how we define our system, we get two completely different but totally correct answers. In one view, energy goes up. In the other, it's conserved. It really is all about your perspective.
Okay, I think we've got the fundamental principle down. So now let's see how it holds up when we start adding more forces back into the mix. Let's start with a spring.
So let's imagine our block falls and lands on a spring. Now, if we define our system as just the block and the Earth again, that means the spring is an external force pushing on it. Think about it. As the block squishes the spring is pushing up while the block is moving down. They're fighting each other. That's the definition of negative work. So the spring is literally sucking mechanical energy out of our block Earth system.
But you know what's coming, right? What if we just redefine our system one more time to include the block, the Earth, and the spring? Well, now the whole dynamic changes again. The spring force becomes internal. And because the spring is what we call a conservative force, just like gravity, the work it does is simply stored as potential energy. With no other external forces in the picture, the total mechanical energy of this bigger system is, you guessed it, conserved once again.
But there are some forces that just don't play by these nice, clean rules. I'm talking about things like friction or air drag. We call these non-conservative forces, and you can think of them like a one-way energy leak. See, with gravity, the energy it takes when an object goes up can be fully recovered when it comes back down. But the energy lost to friction, that just turns into heat and sound. It's gone. You can never get that mechanical energy back. It just doesn't conserve it.
Okay, so let's just pause and put this all together into a quick little cheat sheet.
For a conservative force, like gravity or a spring, it only conserves energy when it's inside the system. But for a non-conservative force, like friction, it's a game changer. It always changes the energy. It doesn't matter if it's inside or outside your imaginary box. This right here is the toolkit we need to finally go back and solve that puzzle from the beginning. All right, with these rules in our back pocket, we are finally ready. Let's head back to that complicated machine and solve this puzzle once and for all.
Okay, analysis number 1. Let's define our system as just the 2 blocks and the spring. Notice what we're doing here. We are intentionally leaving the Earth out of the picture for now.
So, what forces are acting on this system from the outside? Well, you've got gravity, pulling down on that hanging block. It's helping the motion, so it's doing positive work, pumping energy in. At the same time, you've got friction on that top block, creating drag. It's fighting the motion, so it's doing negative work, pulling energy out. Now, since the whole thing moves, we know the pull of gravity is winning that tug of war against friction. So the net work being done on our system is positive.
And since the net work being done on the system is positive, the answer is crystal clear. For the system defined as just the blocks and the spring, the total mechanical energy increases. Period.
But what happens if we shift our perspective one last time? Let's zoom out. Let's define our system as the whole shebang, the 2 blocks, the spring, and the Earth. And here, right here, is where the answer completely flips. By adding the Earth to our system, gravity instantly becomes internal. We don't count its work anymore, it's just part of the system's potential energy. So what's left? What's the only external force still doing work? It's friction. And as we know, friction always does negative work. It's always removing energy from the system.
And that means, for this bigger, all-inclusive system, the only external work is negative. Therefore, the total mechanical energy must decrease. It's constantly being bled away as heat by that pesky friction.
So there you have it. The exact same machine, running the exact same way, gives us 2 different, equally correct answers. Energy increases or it decreases. It all just depends on where you decide to draw the line around your system. And that kind of leads to one last big cosmic question, doesn't it? If we define the system as the entire universe, well, there is no outside. So does that mean its total energy is the one thing in all of existence that truly, absolutely must be conserved?